Hello, welcome to another problem session. Today we have an interesting problem that there is a spacecraft that's in a circular orbit about Earth. It could be any planet, but we just picked up for Earth. So this is the pink orbit. It's going in here and it's circular, and the radius of this is 2 times the radius of Earth. This by itself is Earth. And then first one is very simple. What is the speed of this aircraft as going in the circular orbit, assuming uniform speed? And then second one is very interesting. Is suppose you want to put from this orbit, you want to go into that orbit. So you will need to boost the speed at some point, and say you want to boost the speed instantaneously from some value vi to some vf. Of course, it takes time to boost it. Technical details, I don't want to go into it, but so question is how much of a boost you will need at that point if you want to do it at that point. That's what this is saying. Okay, so let's do the A, which is kind of easy. You can do it many different ways. You probably remember from much earlier chapters, circular motion. So this can be done. One way is just do circular motion. So you know uniform circular motion. So you have a m, so vi over the radius of the orbit is 2re. So that's equal to the force on it, and it's g m mass of the Earth over 2re squared. That's the distance from here, center of the Earth, to that. So that's the orbit. That's the 2re. These are all REs. This is REs, radius of the Earth. So this one's very easy to simplify. The m goes away. 2re goes away. And so this thing is just vi and it's a speed, so I just take a plus part, gme over 2re. And we're told that we can use this, a simpler one. So I just multiply by r square and divide by re. So this thing becomes square root of half GRE. So we have all the numbers given, and let me work out the numbers. So I'm going to work out square GRE and then square root of 2. So we're going to work out that number because we're going to get that for the B also. Okay. So we have the answer now. The numerator is equal to 7. Numerator is equal to 7861. 7861 is 1.414, and this thing turns out to be 5559. So 5559 meter per second. So of course all of these decimals are not important because we're already using only 3 decimal places. So this probably I should make it 5,560 meter per second. All right. So A is very simple. Let me erase this and do the B. Okay, to do B, we've already kind of given a formula here that that same major axis of an elliptical orbit is related with energy in this fashion. And we know energy will be equal to half mv, and that's vf, so mvf square gmm over at this point it is a 2re from the center. So this will be potential energy and this is the kinetic energy. So this is kinetic energy and this whole thing is potential energy. And from this formula, this would be equal to minus g, this mass of the earth, m over 2 times same major axis. This is the entire axis from here to there, that's 2a. So this from here all the way here is 2 times a. Okay, so we got this equation and we need to figure out Vf so we can see what the boost is needed. Okay, you can see in this equation a couple of things you can notice. M goes away from every term, so I don't need to know the mass of the satellite. This thing is 5 Re, and this term is going to combine. Let's multiply by 2 just while we're at it. 2 goes away from here and ends up here. So you can see Vf square going to be this whole thing GME over RE common 1 minus 2 over 5, which is 3 over 5. And so this whole thing is G times RE, and this is 3 over 5. So the Vf will be square root of 3 over 5 times GRE. And let me see what the answer I get. So I get 6090 meter per second. Therefore, Vf minus Vi is going to be this minus that, that's 30. Let me see, 6090 minus 556. You're not going to be total 30. This is 30, and then 5. So it's actually 530 meter per second. So that's the boost I need to make. Now you can extend this. So if I knew the mass was given to be 4,000 kilogram, and the question would be what kind of energy needed to do that. You could extend in further ways. Will be new angular momentum. You can also extend it to look at, say, if you were going to do with throwing part of this, say, if you make a 400 kilogram, 10% of this, eject. Suppose you were to do the eject over, say, 20 seconds. What kind of force, thrust force that you'll need to develop. to actually 20-second or maybe some time period t that you need to get that. I mean, this, or you could say this is, I need to get some m kilogram for some time. So what are the combination of these two that I need to have to satisfy that this much increase in the velocity in the same direction, right? So these are some of the questions that you can explore. I'm going to stop here. This is a pretty simple, nice problem, and you can recognize that this is coming from our study of the elliptical motion for two-body problem. So I think I'm going to move on from now, go to another series of concepts starting tomorrow. So see you around. Bye.